Hello and welcome to the second lecture on routing in packet switch networks. In the first lecture, we have discussed the basic issues related to routing in packet switch networks, particularly why routing is needed, what are the parameters to be considered when you design routing algorithms, and various constraints. And we have discussed two important routing techniques such as fixed routing and flooding. So, in this lecture we shall continue our discussion on routing techniques, and here is the outline of today's lecture. So, we shall start with random routing, and then we shall consider flow based routing, which is again one kind of fixed routing technique, fixed or static routing technique. On the other hand, distance vector routing and link state routing, these two belong to the category of adaptive routing. We shall also discuss about multicast routing. Finally, we shall consider the routing algorithms used in ARPANET as a case study. ARPANET, as you know, is the foundation of internet technology. Based on various approaches, tools and techniques were developed in ARPANET, that is your Advanced Research Program Network, Research Program Agency Network, and there various techniques were developed, and we shall discuss and see how the routing algorithm evolved as part of ARPANET. And here is the what will the students will learn. On completion, the student will be able to understand the function and utility of the following routing algorithms: random routing, flow based routing, distance vector routing, link state routing, and multicast routing. And also they will understand how routing algorithms evolved in ARPANET. So, let us start with the various routing techniques. As I mentioned, we have already discussed fixed routing and flooding, and in this lecture we shall consider the other approaches. And as I mentioned, a large number of routing strategies have evolved over the years, and here is a list of the important ones, and we shall consider these techniques in this lecture. Let us start with random routing. So, this can be considered as a special case of flooding. We have already discussed flooding, and we have seen in flooding it leads to too many packets, and also it leads to too much load on the network. So, that can be somewhat reduced with the help of this random routing, and it has the simplicity and robustness of flooding with far less traffic. So, it gives you some benefits of flooding, at the same time it reduces or overcomes some of the limitations of flooding. That means, it reduces the traffic load, which is the main drawback of flooding. What is being done? A node selects only one outgoing path for transmission of an incoming packet. So, suppose let us consider a particular node in a subnet, and suppose this is the link through which a packet has been received, and these are the outgoing links, various outgoing links. As we have seen, in case of flooding, if a packet is received here, it is transmitted forwarded on all these routes, on all the links except through which it has been received. But in random routing, that is not done. The outgoing link is chosen at random, excluding the link on which the packet has arrived. That means, it is not sent through this path, but not only that, it sends through one of the three paths. It may be at random. Now, you may ask, how do you do it? If you do it at random, there is no need for any other information of the present state of the network. whether how many packets are in the queue or what is the bandwidth of the link. It can be done on that way. Another possibility is that you can do it in a round robin fashion. That means whenever you send, whenever there is no other criteria, you may choose one of the links, next time you may choose the another link, next time you choose another link. In this way you send through all the paths one after the other. So, you may call it round robin technique. So, in this case it will distribute the load evenly on different links, but unfortunately this has a limitation. Limitation is that some of the packets may get forwarded in the direction of the source rather than the direction of the destination. That can be overcome by using some approach, or another refinement is to assign probability to each outgoing link and to select the link based on probability. That probability can be computed based on maybe data rate. Let us consider, say suppose these are the this is the input, I mean link through which the packet has come, and these are the 3 outgoing links. Now, let us assume the rate of transmission on these links are R1, R2 and R3. Then probability Pi of sending through a particular link can be computed in this way. Pi is equal to Ri, that means the rate of transmission through a particular link, by summation of all the Ri's. That means in this particular case here it will be R1 plus R2 plus R3, that will be in the denominator, and in the numerator it will be one of the links. Then based on this the probability is calculated, and the link having the highest probabilities is used for transmission. That means here what is being done, the packet is forwarded in a particular direction, and for that the probability is calculated based on the bandwidth of that link. So, higher the bandwidth, that is being preferred for transmission. So, it can be done in this way also. The actual route will typically not be the least cost route. So, whenever you do it in this manner, you cannot guarantee that the route that will be chosen is least cost route, because we are not considering the cost of different routes in a systematic manner. As a consequence, the transmission of packet will not go through the least cost path, and as a consequence the load on the network will be higher than the optimum traffic load. So, we find that this random routing does not use any other information. It can be purely random, or it can be round robin, or if some information is used, that can be the data rate of different links. And it has the advantage that the traffic in the network is significantly lower than the flooding. However, it has the robustness, because it is sending through a particular path. That means ultimately the packet will be delivered to the destination like flooding. So, it has the robustness and simplicity of flooding, but with much reduced traffic load. So, this is random routing. Then comes the another important routing algorithm, that is flow based routing. So far in fixed routing we have seen only the topology of the network is taken into consideration. We have seen that the nodes are connected to different links, and for each of these links either the queue length or the delay or the transmission time, I mean the actual data rate, these are being used, but not the information about the load or the flow. Now, what can be done? In addition to the topology, information about the load information about the load can be used for routing, and a concept of flow is used here. A flow can be considered as, I mean flow is between a pair of nodes is relatively stable and predictable. That means if you know that the traffic through a particular direction, and if the data rate of a particular link is known, very easily the flow between a pair of nodes can be calculated. So, for a given capacity, that means the data rate of a particular link, average flow is known. It is possible to compute the mean packet delay using queuing theory. So, queuing theory can be used to compute the mean packet delay for each of the links, and from the mean delays of all the lines, it is easy to calculate flow weighted average to get the mean delay for the whole subnet. So, once you get the mean delay of the whole subnet, that can be used for finding out the least cost path by using that that Dijkstra's algorithm that we have discussed in detail. So, using that, again a routing table is calculated, and based on that the minimum average delay path is chosen. So, again it can be considered as a fixed routing, fixed or static routing. However, here we are taking into consideration not only the information about the topology, but load information, and it is based on flow. So, this is another example of fixed routing that we have discussed here. Now, we have seen that the static or fixed routing techniques has serious limitation, particularly when the network is not stable. What happens? There are two principal conditions that affect routing decisions. One is failure. So, when a particular node fails, obviously you cannot pass packet through that, and obviously you have to reroute the traffic in some other direction. So, when a node or trunk fails, that means not only the node, a link or trunk may fail, it can no longer be used as part of the route. So, in this condition, obviously the fixed routing will not work, because fixed routing will always use the routing table, which does not take into consideration the failure of a node or a link. Another possibility is that is congestion. We shall discuss about congestion in the next lecture in details, and we shall see that when a particular portion of the network become heavily congested, it is desirable to route packets around the area of congestions. So, normal that traffic that the traffic is used for controlling the vehicles. We have seen whenever there is a traffic jam in a particular area, usually the cars or other vehicles are diverted through some other route. So, the same technique has to be used here. It is necessary to reroute the traffic such that it does not go through the congested area, but around the congested area, and that is the adaptive routing. So, the adaptive routing will keep on modifying the routing table or whatever it may be, so that the dynamic conditions because of failure and congestion is taken care of. And the classification of these adaptive algorithms can be done based on the information source. There are three alternatives about the information source. Information source can be purely local. So, in such a case, what is being done, information is gathered from that node itself. That means it may be the queue length on different links of a particular node. So, in that case it is purely local. That means how many packets have been accumulated in each of these links. So, this is a purely local information that can be used for routing. Another possibility is that we can use adjacent nodes. That means each node can gather information from its neighbors to which a particular node is directly connected. So, that can be used for routing. In such a case, we call it information gathering is taking place from adjacent nodes. Another alternative is the information can be gathered from all nodes. So, in a packet switch network, there may be many nodes. So, each node will gather information from all other nodes. As in such a case it is a more global hub. Obviously, whenever it is more global, more information has to be gathered. It will take more time, it will put more load on the network, because whenever you gather information, obviously exchange of packets will take place, that will put some load, and also the node has to do computation to I mean for using the information gathered from all nodes for the purpose of routing. So, classification can be done based on these three approaches. Then for adaptive routing to be possible, network state information must be exchanged between among the nodes, as I mentioned. Now, you may be asking what kind of metric can be used for the purpose of routing. One simple approach is to use number of hops. So, from a particular source to a destination, the information about the number of hops, that the number of nodes to be used for relaying or retransmitting the packets, forwarding the packets, can be used as a metric, and this is possibly the simplest metric that can be used. However, this particular metric is not commonly used. Second metric that can be used is the time delay in millisecond. So, this time delay in millisecond can be used. However, how do you get information about the time delay? One representative of this time delay information is the queue length. One can use the queue length for each outgoing link towards a particular node. So, that can be used. Another approach is that delay can be actually measured. So, based on that, the time delay can be used, and the total number of packets queued in the path. So, here it can be as you can see, it can be a more global approach. Here what you are doing, the packet queued along the path in the from source to destination is used as a metric for finding out the route. Now, here we find there is a trade-off. More information exchange you do, that means if the information is more global, if you gather more information, there is a possibility that routing strategy will be better. On the other hand, if it is based on local information or no information, as you have done in case of flooding and random routing, then the routing strategy may not be very good. So, what is happening, whenever more information exchange is used for better routing, that increases overhead. So, we find that it is essentially a trade-off between better routing and more overhead. That means, if we want lesser overhead, then we cannot get better routing. On the other hand, if we want better routing, your overhead on the network increases. Another important parameter is frequency. That means, if it is more frequent, you can perform better routing, but it will be more overhead. That means, if the information gathering take place more frequently, then obviously the routing will be better. On the other hand, if the information gathering takes place after a large interval, then the information that means the routing that is being done based on the information may not be very relevant. By the time that information is used for routing, the network parameter may change. So, more frequent it is better, but increases the overhead. So, these are the trade-offs that has to be that will be encountered whenever you design adapting routing algorithm. So, as a consequence, it will be quite complex. And there are two very popular approaches for adaptive routing. One is known as distance vector routing, another is link state routing. We shall discuss about them in details in this lecture. But before that, let us take up a very simple example of a adaptive routing technique. It is essentially a local approach, and that is why it is known as isolated adaptive routing. In this case, a node routes an incoming packet to the outgoing link with the shortest queue length Q. So, if based on the queue length in different paths, the routing is done. So, basic idea is that it will do the balancing of the load on outgoing links. So, the chosen outgoing link may not be heading in the right direction. Unfortunately, what can happen, whenever it is based on the queue length of different links, then there is a possibility that a packet will be headed towards the source rather than the destination. How do you take into consideration that? So, to take direction into account, each link emanating from the node has a bias. So, the basic approach is modified and a bias is used for each destination I. Now, for each arriving packet heading for a node I, the node would choose the outgoing link that minimizes Q plus Bi, that means Q length and the bias, these two are added together, and after doing that, which minimizes Q and Bi, is used for linking. And so, whenever you do that, a node would tend to send packets in the right direction with a concession made for the current traffic delays. That means, this Q factor, it takes into account the current traffic delay. On the other hand, this Bi, that is your bias, is being will try to send in the right direction. Let us take up an example for that. Suppose here we have considered the node A in this network, and with the destination address 5. That means, a packet is going from node 2 is here towards 5. So, from 2 it is going to 5, and this node 4 in between is shown here. As you can see, the node 4 has got 1, 2, 3, 4 links, and the queue length on different links towards node 2, node 4, 6, node 5 and node 3 are shown here. So, queue length towards 2 is 2, towards 6 is 1, towards 5 is 4 and towards 3 is 3. On the other hand, there is a bias table. As you can see, bias 2 is towards 2 is 7, because it is going in the direction of the destination, direction of the source. That is why here the bias is more. On the other hand, towards 3, if it goes, bias is 6, because again it is going away, and on the other hand, if it is going in this direction, bias is 0, and whenever it is going in this direction, again it is going little off, so bias is 3. So, if you add, that means in this from 2 plus 7 it is 9, 1 plus 6 it is 7, 0 plus 4 it is 4, and 3 plus 3 it is 6. So, again it is directly delivered to 5, because although 4 packets are there, but because of 0 bias it is directly forwarded to 5. So, we find that if the only the queue length was used, then the packet would have been forwarded towards 6. That means, in this direction, then it would have come this way. So, it would have taken a longer path, but that is being avoided because with the help of the bias. So, because of 0 bias, the node is node 4 will forward it directly to 5, and although the queue length is 4 here. So, we find that by using local information and also by using suitable bias, it has been possible to do the routing in a effective manner in this isolated adaptive routing. Now, as I mentioned, the one of the most popular adaptive routing technique is distance vector routing, and these are the key characteristics of distance vector routing. So, in distance vector routing, knowledge about the entire network is gathered and routing only to the neighbors. However, the routing is done only to the neighbors, and that is why here you find there is a I mean, here you will find that the table is maintained, and based on the information sharing at regular intervals. So, these are the 3 basic features of this. First of all, knowledge about the entire network is gathered, and routing is done only to the neighbors, and information sharing is performed at regular interval. And based on that, each node maintains a routing table having only one entry for each node with two other fields. So, this is essentially the address of the destination node, address of the destination. And here the cost is computed based on the information that is being gathered, information sharing at regular interval. That information that is being gathered is stored here, and with the help of this, the preferred next node, this is the next hop node, this is the next hop node that is being mentioned. So, from this table, each node gets the information about the cost and also the next stored node, and based on this cost information, the routing can be performed. The routing can be used based on that Bellman-Ford algorithm or some other least cost path algorithm. So, in this way, the table, the node maintains a routing table, and the minimum cost route is used for routing purpose. This is the distance vector routing. Then comes the link state routing. In link state routing, the basic steps are: identify the neighboring nodes, measure the delay or cost to each of its neighbors. So, here as you can see, in the previous case what was done, the knowledge about the entire network was gathered in distance vector routing. So, a vector is being maintained, distance and cost vectors are being maintained here. On the other hand, here only information about the measure, the delay or cost to each of the neighbors is computed. Then form a packet containing all the information and send the packet to all other nodes. So, in the previous case, what was happening, the information was sent only to the neighbors. On the other hand, here the information is being sent to all the nodes, and obviously it is being done by flooding. So, send packet to all other nodes. So, here although information gathering is taking only from the neighboring nodes, but the distribution of information is taking place to all other nodes. So, compute the shortest path to every other node by using Dijkstra's algorithm. So, in this case, the information is gradually gathered based on the information received from all other nodes, and then the routing is being done. So, basic idea is, as you can see, it uses knowledge about the neighborhood and then routing to all by using flooding, as we have seen. So, it uses flooding to send the information to all the nodes, and information sharing is performed at regular interval, just like your distance vector routing. And this link state packet, this is being sent to all the other nodes. This is the advertiser ID, that means who is sending the packet, because as we have seen, although information gathering is taking place from the neighborhood, it is being sent to all other nodes. As a consequence, the nodes should know who is doing the advertisement or who is passing on the information. So, this advertiser ID tells each node from where the information is coming, and the network ID is essentially the destination node's address, and cost for transmission is given here for that destination, and that is the next hop node is number ID is given here. So, this 4 information is used, and that packet is known as link state packet. So, link state packet is broadcasted with the help of flooding to all the nodes, and all the nodes will gradually gather information. Initially it may be very sparse, but as time passes, as more and more information is received from different nodes, then each and every node will make some kind of database, and they will use that database for as I have mentioned, the database will be used to find out the shortest path to every other node, and then the Dijkstra's algorithm is used to find out the shortest path I mean first the for each link is obtained, and then the shortest path is obtained to every other node by using die-Custer's algorithm, and that is being used for routing purpose. So we find that this link state routing is quite powerful, and here let us make a comparison between the link state versus distance vector routing. So, link state algorithm converge more quickly and are somewhat less prone to routing loops than distance vector routing. It has been observed that the link state algorithms which I have discussed just now converge more quickly and are somewhat less prone to routing loops than the distance vector routing. However, link state algorithms require more CPU power and memory than distance vector algorithms. Link state algorithms therefore can be more expensive to implement and support. As we have seen, the link state routing, in case of link state routing, the nodes are gradually gathering information and for making a database, and database will require lots of memory. Then they have to do the computation on the database, and they will, each and every node will use the die-Custer's algorithm to get the least cost path to for each of the destination node, and as a consequence it will be little expensive, and it is to implement and support. However, link state protocols are generally used, particularly they are more scalable for this than distance vector routing. So, linked state routings has been found to be more scalable compared to distance vector routing, and that is why the linked state routings are becoming more and more popular. So far we have discussed about three adaptive algorithms. First one was that isolated adaptive routing, which uses local information, and on the other hand the distance vector routing uses information from the from the neighbors, and the distance vector routing gathers information from all the nodes. And we find that the routing decisions is more complex, more processing burden on the switching nodes. That means compared to fixed routing or flooding or random routing, we find that adaptive routing are more complex, and obviously they will put more and more processing burden on the nodes. So, it depends on status information that is collected at one place, but used at another. So, what is happening, the information about the network status, queue length, delay or whatever it may be, is being gathered at different nodes in the network. However, the decision has to be taken in the not in the nodes, but in the stations or computers. So, as a result, they have to be transmitted to them, and that increases the traffic overhead significantly. And it may, if it reacts too quickly to changing network state, it may produce congestion producing oscillation. That means, if the adaptive algorithm is, if it reacts too quickly, what happens? It may lead to congestion producing oscillation, somewhat like this. Suppose there is a traffic jam in a particular part of the city, and very quickly all the traffic is diverted to another part of the city. So, very quickly there will be traffic jam in that another part of the city, and so this way the traffic will hop between two areas instead of going to the destination. So, somewhat similar situation can arise here. This is known as thrashing situation. So, so this thrashing situation has to be avoided, and that may arise in adaptive unless it is carefully implemented. However, in spite of these drawbacks, adaptive routing is widely used because of improved performance and can aid in congestion control. So, although it is complex, although it may lead to some congestion producing oscillation, but adaptive routing is still preferred because it improves the performance of routing, and also it can aid in congestion control. As we have seen in the next lecture, we shall see congestion is a very important aspects of packet switch network, and congestion has to be controlled at any cost, and this adaptive routings will help in minimizing the possibility of congestion. Now, we shall discuss about another type of routing, which is known as multicast routing. So far what we have done, routing is essentially from a source to a destination, so between a pair of stations. But there are situations where a particular node will send to a group of stations, a particular station will send to a group of stations. For example, there is a video service provider who is giving video on demand to a group of people. So, in such a case, a particular video, maybe TV channel or of a movie, has to go to a particular users depending on their demand. So, group of users, not to a single one. This is known as multicasting. So, to do multicasting, multicast routing, each node computes a spanning tree covering all other nodes in the subnet. So, what is happening? Let us see how it is being done. In this case, suppose these 1, 2, 3, these are the sources of different packets. On the other hand, 4, 5, 6, these are the destinations, or we may consider these are the subscribers and these are the service providers. So, video signals are going from these 3 stations 1, 2 and 3. On the other hand, it is going to 4, 5, 6 destination stations. These are the consumers or users. Let us see how the spanning tree works. So, here we find, say, a spanning tree is formed from 1, it will go through this path 1 to A, this node A, to node C, node D, and from D it is multicasted. It is transmitted not in one direction, not in one direction, but in 3 directions, because 4, 5, 6, these 4 users are the group of people, group of stations, those they want to get the service. Similarly, from another source it can be, say, from 2, 3 and this path is common, and then it will go to 4, 5, 6. So, from these two stations service can be taken by 4, 5, 6, and so spanning tree is formed. So, what we find that when a packet is sent, the first router examines the spanning tree and prunes it. So, here as you can see, after this node A receives a packet maybe related to a video, then instead of sending to G, it prunes it. So, it simply uses this path and sends it. So, in this way, the whether it will send in a particular direction, that is based on the spanning tree. That means, from A it will go to C, C also will not send to any other path, it will send only in this direction. So, spanning tree formation can be done, and that will decide the route, and multicasting is done. And here as you can see, D will send to all the through all the links, because there are subscribers connected to E, F and directly to D. So, this is the example of multicast routing. And one very important situation, one very special situation of this multicast routing is your broadcasting. So, suppose a particular node has to broadcast some information to all other nodes, and for that the obvious candidate is flooding. So, flooding can be done for whenever the broadcasting has to be done to all the nodes. So, here for example, if this node wants to broadcast something, it will do the flooding and it will reach all the stations. So, in that case the routing algorithm will be simpler. There will be no need to form spanning tree, or the processing needed in each of the nodes will be smaller. However, we already know the limitations of flooding that will be there, but it is a very robust technique for broadcasting. So, that is why flooding is used in many situations for broadcasting purpose. Now, we have discussed various routing techniques, both static and dynamic techniques. Now, let us take up a case study. We shall study the ARPANET network, and we shall see how the routing technique has evolved in ARPANET gradually. And as you know, ARPANET, the Advanced Research Project Agency Network, that is the foundation of the present day internet, and many tools and techniques have been developed in ARPANET which are still being used in present day context. Now, the first generation algorithm was based on distance vector routing, which I have already discussed. It was developed sometime in 1969. So, this first generation algorithm, as I mentioned, it is a distance vector routing. As you already know, it is a distributed adaptive routing. So, there is no central controller, all the nodes take part in routing. So, it is a distributed adaptive algorithm using delay as the performance criteria. So, each node maintains their distance vector, as you can see, maintains two vectors di, di1, di2, din. So, this is one vector. Essentially, this is the delay information for sending packet to node 1, 2 to n, and S is the Si is the it gives you the succession node vector to node I. So, here as you can see, the succession nodes, list of succession nodes are given here, Si1, Si2, Sin, the to where succession node for node I, to where it has to a packet has to be forwarded for sending to destination 1, 2 and n. So, here di is the delay vector and dij is the current estimate of the minimum delay from node I to node j. That means, from node I to node 1 to n, in this way node 1 to 1 to n, this information, this vector is stored. Similarly, the Sij is the next node in the current minimum delay route for the from I to j. So, that means, based on the delay information, the next hop node is calculated, and these two vectors are stored in each and every node. And obviously, for doing that, some calculation has to be done. Periodically, each node exchanges its delay vector with all of its neighbors. As we have seen in distance vector algorithm, we have already discussed, the exchange of information takes place with the neighbors, not with all the nodes. So, that is being done here, and the interval, as you can notice, it is very frequent at the interval of 125 millisecond. And using the incoming delay vectors, a node k updates its vectors as follows. So, it finds out the minimum delay path for all I in A using Skj is equal to I, using I that minimizes the expression above. So, this expression that minimum value is calculated. Here A is the set of neighboring nodes from k, and IKI, that is IKI is the current estimate of the delay from k to I. So, the minimum value is taken as the delay information, and which is being used to compute the least cost path, maybe by using that Bellman-Ford algorithm. Here the estimated link delay is simply the queue length for that link. So, we have already seen, say suppose this is a particular node, and these are the links, outlinks. So, the queue length in each of these for each of these links is being used as a representative of the delay. So, in building the new routing table, a node will tend to favor outgoing links with shorter queues. So, in the link in which the queue length is short, obviously whenever the new routing table is made, a node will tend to favor the outgoing links with shorter queues. Since queue lengths vary rapidly with time, a thrashing situation may result, as I mentioned earlier. So, whenever this thrashing situation occurs, because by the time the next routing table is formed and packet is forwarded, that queue length had changed. And so, what can happen, again the routing calculation has to be done. So, a packet continues to seek out areas of low congestion rather than aiming towards destination. So, suppose this is this is part of the subnet, this is part of the subnet. So, initially this part of the subnet, the packets are forwarded in this direction because of smaller queue. So, there will be congestion here, and whenever it is found that queue length has increased, it is forwarded in this direction. So, there will be congestion here. So, instead of going towards destination, and this condition is known as thrashing, as I have told. So, this is the problem that can arise in ARPANET first generation network. So, whenever the second generation approach was decided, the drawbacks of the first generation algorithm were evaluated. The drawbacks are only queue length were considered and not the line speed. And of course, when the first generation technique was developed, in those days the links were of low bandwidth, low data rate. However, when the second generation network algorithm was considered, by that time the links have changed, have been upgraded from low rate to high rate, and as a consequence it was necessary to take into consideration the line speed. And as I mentioned, queue length is only an artificial measure of the delay. It cannot be a correct representative of the delay, and processing time of a packet before placing it in the queue may itself be variable. That means that queue length may change by the time the processing is being done by a node to send it in a particular queue. So, the algorithm responds slowly to congestion and delay. As a consequence, delay increases. So, these were the limitations which were identified when the first generation algorithm was considered, and second generation algorithm that was proposed in 1979. After 2 years, they shifted to link state routing. So, they modified the distance vector routing and to a link state routing. So, here also the distributed, as you know, the link state routing is also a distributed adaptive algorithm, but which uses the actual delay as the performance criteria rather than that artificial delay based on the queue length. So, the delay is measured directly by timestamping the packets using the positive acknowledgement. For example, if a node receives the packet, so that incoming time is time stamped, and when it is going out, that time is also time stamped, and the difference of that is added with the transmission time and the propagation time of a packet to get the information about the delay, and that delay is being used for the purpose of computation. So, and here as you can see, compared to 128 millisecond, here at every 10 seconds a node computes the average delay on each outgoing link. So, here it is done by flooding, as I mentioned earlier in distance link state routing. Here the interval is significantly increased from 128 millisecond, it is increased to 10 second. So, at the interval of 10 second, by flooding the information exchange take place. Since the interval is quite long, this will not affect much the performance of the network. So, the problem with the previous approaches were that every node was trying to obtain So, second generation. So, by using this second generation algorithm, by measuring the actual delay, the performance was significantly improved. However, when it was again reviewed in the year 1989, it was found that problem with the previous approaches was that every node was trying to obtain the best route for all destination, and that efforts conflicted. That means, since all the packets the nodes were trying to forward in the direction of the least cost path, and best effort routing was done, that was leading to some problem. And it was concluded that under heavy loads, of course, whenever it is node is lightly loaded, network is lightly loaded, it works fine. However, under heavy load condition, this best effort routing or routing in the least cost path direction does not work well. So, the goals of routing should be to give the average route a good path instead of attempting to give all routes the best path. So, instead of using the best path, the good path was computed based on basic approach was not changed. However, there was change in policy. Instead of forwarding towards the best path, it was rather forwarded towards good path. As a result, the network or the subnet towards the best path will not get congested. So, the designer decided that it was unnecessary to change the overall routing algorithm. It was sufficient to change the function that calculates the link costs. So, link cost calculation was done a little in a different way, done in a way to damp the routing oscillations. As I said, that congestion producing oscillations are stopped here, damp oscillations and reduce routing overheads, unless use a simple concept from queuing theory. So, queuing theory was used to find out the link costs. The average cost function is used is to use utilization rather than the delay. Here earlier the delay was used as the main parameter. Here, however, the utilization was considered as the main parameter. So, whenever the load was small, it was essentially based on that distance vector routing. It was somewhat like this. That means, as the utilization is initially small, then it was based on the distance vector routing, and then as the utilization increases, it goes in this region. Here, for example, say utilization is 1, normalized 100%. So, whenever it goes in this region, then it switches to that based on utilization, it switches to that link state routing, and as a consequence there was significant improvement in performance. So, we have discussed about the ARPANET, and we have seen how the routing strategy has evolved in ARPANET, and now it is time to consider the review questions. First question is, in what way random routing is superior to flooding? Second question is, why adaptive routing is preferred over static routing? Third question is, what are the limitations of adaptive routing, LVAR routing? Compare and contrast distance vector routing with link state routing. Fifth question is, in what way second generation ARPANET algorithm differs from the first generation ARPANET routing algorithm. So, these questions will be answered in the next lecture. And here are the answer to the questions of lecture number 12. First question was, why routing is important in packet switch network? As I mentioned in the last lecture, the path to be followed by a packet is introduced in a packet switch network is decided by the routing algorithm. So, since the packets will be making several hops before it reaches its destination, routing is very important, and routing tries to find out the least cost or the optimized path between source and the destination stations. If routing is not done properly, delay increases, and this may lead to congestion. Second question was, what are the primary conditions that affect routing? As I have seen, if there was no change, if everything was static, then static routing is good enough. However, there are two important factors that changes. One is failure. Whenever a node or trunk fails, it can no longer be used as part of the route. So, we have to go for dynamic algorithm. And second aspect is congestion. So, whenever a particular portion of the network becomes heavily congested, it is desirable to route packets around the area of congestion rather than through the congested area. So, these are the two primary conditions that affect routing, and routing strategy are to be changed whenever these two happens. Question number 3 was, what is flooding? Why flooding technique is not commonly used for routing? As you know, flooding is one of the non-adaptive routing techniques where no network information is used. In case of flooding, as each node receives a packet, it is retransmitted or forwarded to all links connected to the node except the link through which the packet has arrived. Flooding is not commonly used for routing for the following reasons. As we know, flooding leads to unbounded number of packets. It may lead to congestion in the network, and a number of copies of the same packet is delivered to the destination node. These are the limitations. Question number 4 was, in what situation flooding is most appropriate, how the drawbacks of flooding can be minimized. Flooding is most appropriate in some critical operations like military network because of its robustness. In flooding, routing technique is the packet delivery is technique. The packet delivery is guaranteed if a path exists. See, drawbacks of flooding can be minimized by the following two ways. As we have seen, one can be done by using that while forwarding a packet, the packet, each node should find whether a particular packet has been already transmitted. If so, the second transmission of the packet should be stopped. Another is hop count. Hop count information should be maintained at each node. The packet is not forwarded if hop count is more than the specified limit. So, with this we come to the end of today's lecture. Thank you. Hello and welcome to today's lecture on congestion control in packet switch networks. In the last two lectures, we have discussed about the routing techniques used in packet switch networks. So, after routing, another very important aspect that has to be considered is the congestion in the packet switch network. And here is the outline of today's talk. First, we shall discuss about why congestion, rather why congestion arises at all. Then the common causes of congestion, or in other words the sources of congestion, we shall discuss about it. And whenever congestion take place, what are the effects of congestion on the packet switch network, that will be discussed. And we shall discuss about two basic approaches for controlling congestion. One is open loop techniques, another is closed loop techniques. Under the open loop congestion control techniques, we have two important algorithms. One is known as the leaky bucket algorithm, another is the token bucket algorithm.